because it will come up when we further discuss superstring theory. Because remember, superstring theory's motivation is to be a grand unification theory, a theory that can be a broader theory that can encompass more things like particle physics, gravitation, electromagnetism. So, and particle physics meaning including quantum mechanics, of course. Quantum mechanics success leads to particle physics. So if you're going to understand superstring theory, which is a requested topic on this channel, we have to keep in mind that when we discuss it, we have to keep in mind that it has to explain quantum mechanics and particle physics. And that's why I wanted to talk a little bit about quantum mechanics. And somebody had asked yesterday about the quantum states and spin. And spin is a quantum property. It's one of the states or properties of a particle. When identified, it helps you with the identity of that particle. Other such properties being mass and charge. It's like asking 20 questions or playing Guess Who. If I told you the mass, the charge, the spin, you could tell me you're talking about the electron, or you're talking about the photon, or you're talking about the W boson. Okay? Is that helpful, Reese? Is light a wave or a particle or both? It's both. Light has wave-particle duality. Let's talk about that. Light has wave-particle duality. Now, so light is both a particle and a wave. At long wavelengths, light is more like a wave. And at short wavelengths, light is more like a particle. What do I mean by that? As you know, light is possible to be found in various wavelengths, and or same as saying various frequencies. Longer the wavelength, shorter the frequency. Because the speed of light in vacuum is a constant. So since wavelength and frequency, the product of that will give you the speed of light in vacuum. Those are kind of they're inversely related. Longer the wavelength, shorter the frequency. Smaller the frequency. So for example, radio waves are longer wavelength type of light. Radio waves are still light. Microwave, my microwave that cooks most of my food is still light. Visible light, which most of our eyeballs can only see visible light, that's still light. UV rays from the sun is still light. Gamma rays from certain astrophysical events that I like very much are still light. X-rays that are needed in the hospital are still light. These are all types of light. It's the same light, it's still light, but it has different wavelength. It's a different wavelength or a different frequency of light. So when you ask, does light have wave-particle duality? It does. It has wave-particle duality. But you can keep in mind that when you're considering longer wavelengths like radio waves, light will have more of a wave-like nature. When you're considering very short wavelengths like gamma rays, light will have more of a photon nature, more of a particle nature. So if you have super small wavelengths, that will be like super high frequency. Super small wavelength, super high frequency. Like say if you're a Geiger counter, you're constantly getting hit by gamma rays, right? That frequency of getting hit by light particles, it's almost like a wave number at this point. It's almost like a number at this point. You're not so worried now about the wavelength of this light. In other words, the wave nature of light, but you're more worried about, well, how many times did my Geiger counter get hit with this event of gamma rays? And you count that, and that is utilizing the particle nature of light. So light has both particle and wave nature. Depending on your experiment, you might want to leverage its wave nature or its particle nature, depending on the wavelength of your experiment, depending on the sensitivity of your experiment, and depending on the event of interest. Okay?